All right, hello everyone. How are y'all today? Hope you're doing well. Today we're going to talk a little bit about chemical reactions, and then we're going to kind of proceed this into enzymatic reactions. So everything that happens inside you, organisms in general, um, is going to require some kind of chemical reaction. So in a chemical reaction, it is a process by which we change one set of chemicals into another. So if I can just use like letters, so let's say we have A and B plus C and D go to make a C and B. Whoops, ran out of space. D. Okay. So you can see here, and you'll talk extensively about this in chemistry next year, where A used to be bonded with B and C was bonded with D, and now they kind of switched. All right. So it is the breaking of bonds and the reforming of bonds is really what we're talking about. So the reactants in any chemical equation are what comes first. Okay. So these are the things that are before the arrow or what we are using to make our product being what comes after. So these are our products, these are our reactants. Products, I always like to think it's kind of easy. Products are the outcome, like you produce something, it's something you made. So that are the things that are made. The reactants are the things that are going to be used to make whatever we're making. All right, so let's talk about a real world example. You breathe in O2, your body goes through metabolism, just the process of where we break down chemicals in order to continue our life and use those. Okay. So in this example, O2 is used as the final electron acceptor, and when we talk about cellular respiration, okay, we'll talk more about that when we get to cell energetics. All right. However, there's a problem. Most chemical reactions in life are either slow or take a lot of activation energy. Activation energy is the amount of energy it takes to get something moving. Okay. So here's your baseline. That's how much energy it takes. Once it gets to there, it goes by itself just freely, like woo. Okay. But we have to somehow make up this differential between here and here. Okay. So your body has come up with a solution over millions of years of evolution, and we have what we call enzymes. Okay. These are proteins that lower the amount of energy it takes to begin a reaction and helps you live a better life. Okay. So once again, it's going to lower that activation energy. So as opposed to having to get all the way to this point, we just have to get to this point. All right. So as I just talked about, activation energy is the amount of energy a reaction is needed. The reaction needs to get going or to kind of freely roll downhill, for lack of a better way to put it. This is the start energy because the more start energy it takes, the more start energy we have to give it before we can get out what we need from it. So it's important for us in our lives to maintain a certain amount of energy. And without enzymes, all the reactions in our body would run at a much higher rate, and we would have to burn much more energy just to get these reactions to occur. All right, so as we kind of alluded to, enzymes are proteins. I will ask you that. Make sure you know that. And they act as a biological catalyst. Biological just means living. Catalyst. A catalyst is anything that speeds up the rate of reaction, all right, without using large amounts of energy. Okay. So here is the normal amount of activation energy. So if I'm looking at this graph, I have to go all the way up to here, putting energy in before the reaction will go and we get to our products. Okay. However, if I add an enzyme, something that's going to help this thing out, can't draw a straight line today. Boom, I only have to get to here. Now, this differential might not seem like a lot, but you have to remember that your body is doing millions upon billions of these reactions all the time. So this little bit times 1 million, because your body's doing this all over it, 100 thousands of different reactions all the time. That's a substantial amount of change in the amount of energy it's going to require to for your body just to do normal body processes. Okay. So if we did not have these enzymes, our bodies would probably run much hotter, much less effective, and not nearly as efficient. You'll notice we end at the same point. We do not, it's not like we end at different points. We get to the same products, same outcome. However, we do it much easier in this method, okay, with the enzymes. Most enzymes end in ACE, ASE. All right, that's an easy way to spot an enzyme. Amylase is something in your saliva that helps break down carbohydrates. Proteinase, something that breaks down proteins. Lipase, something that helps break down lipids. Okay, there's a whole bunch of lactose is broken down by lactase. All right, for those in the lactose intolerant category, unfortunately, your body does not make lactase. So that's why you cannot digest the sugars and therefore get the old bubble gut, as it's called. All right. So enzymes are what we call a lock and key model. They're very, very specific for what they will do. Lactase, since I'm kind of using the lactase only works on lactose. It doesn't go around and find other molecules to try to mix in with and do its thing with. It is only used for breaking down lactase, or lactase is only used for breaking down lactose. They have a very specific active site, which is where the enzyme binds to. All right. To help reduce the activation energy, essentially help to break those bonds. These reactions, the reactants, all right, the things on the left are called a substrate. So you have a substrate and once again the products. Enzyme release the products after the reaction is done and they can start it over and over again. So something key here, enzymes don't live forever, but they're not a one use item. Okay. So they can be used many times. All right. It is not a one and done. All right. So just because this is our substrate, so this would be like lactose. This is our enzyme lactase. Okay. And this is a real good example because lactose is comprised of two sugars that are bonded together. And what happens here is the lactose bonds to the active site. Okay. Once again, where the enzyme binds to, or where the substrate and the enzyme come together. All right. So the substrate, lactose, enzyme, lactase, the active site where they come together. So this is our substrate. This is the bonded product where the enzyme and the substrate are bonded together, and then you end up with your two products here. All right. And your enzyme, as you notice, all right, is more or less perfectly fine. Nothing's really happened to it. It's good to go. All right. So they can go back and forth, left and right, but mainly we're just looking at it from left to right. We can go right to left, but we're looking at it left to right. So we end up with our products, our outcome, the two sugars that it broke it down into, and then our enzyme goes off and essentially does what it just did over and over and over and over and over and over and over again. All right. Enzymes are a type of proteins, like proteins, like we talked about. Their jobs are to regulate body activity without using too much energy, but they can be damaged. All right. Another term for damaged, and we'll use this term, is denatured. All right. It means they're kind of broken apart. There are a couple ways we can denature a protein. So we think of proteins, a bunch of amino acids, as we learned in last section. Amino acid, amino acid. And we don't get too much into this because this is upper level, like honors, not even honors, just more AP stuff. The folding of proteins turned them into something functional. So a protein that is functional will look much more like this than just like a long chain of amino acids. So if it runs into extreme temperature, all right, especially above 100 degrees Celsius, aka boiling, okay. pH, once we work out of a certain range of pH, all right, it becomes not as strong or not as effective. Now, stomach acid is a pH of 1, all right. There are enzymes that are happy with a pH of 1. Um, if you go more neutral, like 7 pH, they are no longer happy, okay. So it just depends on what pH they like. Kind of the same thing with temperatures as well. Some like it hotter, some like it colder. It just kind of depends, but they all have this certain range that they work best in. Cell activators, these are things that are going to turn on an enzyme, so this is going to increase the rate of enzymatic reactions. All right. And inhibitors, okay, kind of in the name, and they're kind of explains it, but activators are going to increase that energy or increase that ability to do what the enzymes do. Inhibitors are going to slow or turn off certain cell activities and allow it to slow down. Sometimes we need more of something, sometimes we need less of something. These activators and inhibitors help with upping the activation or lowering the activation, depending upon what we need. All right, that's it for this one. Of course, I know you're going to have questions, which is perfectly fine. I expect you to have questions. Bring those into class and we will talk about them. Have a great day.